What if humanity's future isn't written in the stars beyond our galaxy, but confined forever to this spiral disk of light we call home? What if the Milky Way isn't just our cosmic address, but our eternal prison? Tonight, we venture into territories where the dreams of science fiction crumble against the immovable walls of physics itself, where the distances aren't just vast, but fundamentally insurmountable, and where our species might be locked into a cage 200,000 light years across for the entire span of human existence. Picture this. You're standing on Earth, looking up at the Andromeda Galaxy on a clear autumn night. That faint smudge of light, barely visible to the naked eye, represents 2 trillion stars, countless worlds, and possibilities beyond imagination. It's our nearest major galactic neighbor, a cosmic island universe separated from us by a gulf that makes the word distance feel inadequate. That photon hitting your retina right now began its journey 2.5 million years ago, when our ancestors were barely recognizable as human, when Homo habilis was just learning to chip stones into tools. Now imagine trying to send a spacecraft there. Not a radio signal, not a message. An actual vessel with human beings or their descendants aboard. The fastest human-made object ever created, the Parker Solar Probe, reaches speeds of 430,000 miles per hour when it dives toward the sun. At that velocity, which required the gravitational assist of our star itself to achieve, the journey to Andromeda would take approximately 3.7 billion years. The sun will have expanded into a red giant and consumed the Earth long before that ship reaches its destination. But Andromeda is close. Cosmically speaking, it's in our neighborhood. The observable universe extends 46.5 billion light years in every direction, containing an estimated 2 trillion galaxies. Most of them are racing away from us faster than light itself, carried by the expansion of space-time, forever beyond our reach, no matter what technology we develop. The universe has placed most of itself behind a one-way mirror, visible but eternally untouchable. This isn't a problem we can engineer our way out of. This isn't about building a better rocket or discovering some exotic propulsion system. This is about the fundamental architecture of reality, about distances so vast that they make a mockery of human ambition, about timescales that dwarf the entire history of complex life on Earth. We're not talking about the challenge of crossing an ocean or even a solar system. We're talking about gulfs so immense that light itself, the fastest thing in the universe, takes millions or billions of years to traverse them. And here's where it gets truly unsettling. What if this isolation isn't accidental? What if the structure of the cosmos itself is designed in such a way that civilizations can never meet, never threaten each other, never share their knowledge or their wars? What if the distances between galaxies serve as a cosmic quarantine, keeping each island universe separate and alone for all eternity? Some scientists have proposed that this might be the solution to the Fermi paradox, the troubling question of why we've never detected alien civilizations despite the vastness of space and time. Perhaps we're all trapped in our respective galaxies, looking out at a universe full of life we can never reach. Tonight, we're going to explore the brutal physics that keeps us confined to the Milky Way. We'll examine the speed limits imposed by relativity, the energy requirements that make intergalactic travel absurdly impractical, the cosmic expansion that's actively working against us, and the biological realities of journeys lasting millions of years. We'll venture into speculative territory about generation ships and digital consciousness, about what it might mean if we could somehow cheat these limitations. And we'll grapple with the philosophical implications of living in a universe where most of everything is forever out of reach. But we'll also find reasons for hope and wonder. Because while we may never leave the Milky Way, our home galaxy contains between 200 and 400 billion stars, each one a potential solar system, each system potentially harboring worlds we could explore. If we're prisoners in a cage so vast that 1 trillion human civilizations could spread throughout it without ever meeting. The question isn't whether we're confined. The question is whether this confinement matters, and what we choose to do within the boundaries that physics has drawn for us. Let's find out why the Milky Way might be humanity's permanent home, and what that really means for our cosmic future. Before we dive deeper into this sobering exploration of cosmic boundaries, if you're fascinated by the ultimate limits of human exploration and the physics that constrains our future among the stars, make sure to hit that subscribe button and ring the notification bell. Drop a comment below telling me what time it is, where you're watching from, and where you're located. I love seeing our global community come together to explore these profound cosmic questions. And if you appreciate the research, calculations, and existential contemplation that goes into these deep dives, a like really helps the channel grow and allows me to continue bringing you content that sits at the intersection of hard science and cosmic philosophy. I want to be clear from the start. What we're discussing today isn't speculation or theoretical physics that might be overturned. This is about the most fundamental limitations known to science, the iron laws of relativity and thermodynamics that govern everything in our universe. But we'll also explore the edges, the places where those laws might permit loopholes, and ask whether sufficiently advanced technology could exploit them. We'll maintain scientific rigor while still allowing ourselves to dream, because that tension between what's possible and what we wish were possible is where the most interesting questions live. This video is longer than most because the topic demands it. We're going to move from basic physics to the far reaches of speculation and back again, building a complete picture of why intergalactic travel represents perhaps the single greatest challenge humanity will ever face. So settle in, and let's continue this journey to the edge of what's possible and the beginning of what's forbidden. Let's start with a number that should make you uncomfortable. 2.5 million light years. That's the distance to Andromeda, our nearest major galactic neighbor. To put that in perspective, a light year is the distance light travels in 1 year at its cosmic speed limit of 186,282 miles per second. That's about 5.88 trillion miles. Multiply that by 2.5 million, and you get a number so large it stops having meaning. 14.7 quintillion miles. That's a 14 with 18 zeros after it? Now, humans have actually left Earth. We've been to the moon, 250,000 miles away, achieved in 3 days with 1960s technology. We've sent robotic probes to every planet in our solar system. Voyager 1, launched in 1977, has traveled about 14.5 billion miles and finally entered interstellar space in 2012. That sounds impressive until you realize it's covered only 0.0025% of the distance to Andromeda in nearly half a century of travel. At Voyager's current speed, reaching Andromeda would take 1.6 trillion years, roughly 120 times the current age of the universe. But surely we can do better than Voyager 1, right? That was 1970s technology, powered by decaying plutonium and limited by the rocket equation that dominated the space age. Let's consider the Parker Solar Probe, humanity's fastest spacecraft, which reaches speeds of 430,000 miles per hour when it whips around the sun. Even at that blistering pace, achieved only through gravitational assist, the journey to Andromeda would take 3.7 billion years. For context, 3.7 billion years ago, Earth was still in its Archean eon, inhabited only by single-celled organisms. Multicellular life wouldn't exist for another 2 billion years. These aren't just big numbers. They represent a fundamental problem with the architecture of the universe. The distance between galaxies isn't like the distance between continents or even stars. We're dealing with a qualitative difference, not just quantitative. When Columbus sailed to the Americas, the journey took weeks. When we sent Apollo to the moon, it took days. When we send probes to the outer solar system, it takes years or decades. But when we contemplate intergalactic travel, we're talking about timescales that exceed the entire evolutionary history of complex life on Earth. The Milky Way itself is about 100,000 to 200,000 light years in diameter, depending on how you measure it and what you count as the galaxy's edge. The Sun sits roughly 26,000 light years from the galactic center, about halfway out along one of the spiral arms. Just traveling from one side of our own galaxy to the other, at Parker Solar Probe speeds, would take 145 million years. That's the entire span from the early Cretaceous period, when dinosaurs dominated Earth, to the present day. These distances create a natural quarantine between galaxies. The local group, our cosmic neighborhood, contains about 80 galaxies, most of them dwarf galaxies with billions, rather than hundreds of billions of stars. Andromeda and the Milky Way are the dominant members. But beyond the local group, the distances become truly staggering. The Virgo supercluster, the larger structure that contains the local group, spans 110 million light years. The observable universe extends 46.5 billion light years in every direction, containing an estimated 2 trillion galaxies, each one a separate island universe. Now here's where the situation becomes not just difficult, but potentially impossible. The universe is expanding. Not just expanding, but accelerating its expansion. Galaxies beyond the local group are moving away from us, and the farther away they are, the faster they're receding. At a certain distance, called the cosmic event horizon, galaxies are receding faster than the speed of light. Not because they're moving through space faster than light, which would violate relativity, but because space itself is expanding between us and them. Light from those galaxies will never reach us, no matter how long we wait. They exist beyond a cosmic one-way mirror, visible now because their ancient light is still arriving, but forever beyond our reach. Even within the local group, the challenges are profound. The Triangulum Galaxy, our third largest local neighbor, sits 2.73 million light-years away. The Large Magellanic Cloud, a satellite galaxy of the Milky Way visible from the southern hemisphere, is a relatively close 163,000 light-years distant. Relatively close, in cosmic terms, still means that light takes 163,000 years to travel from there to here, a span of time longer than our species has existed. What makes this particularly sobering is that, unlike other challenges humanity has faced, there's no obvious technological pathway to overcome these distances. When faced with crossing oceans, we built ships. When faced with flight, we built airplanes. When faced with going to space, we built rockets. Each challenge was immense, requiring decades or centuries of development, but the path forward existed. With intergalactic travel, we're not just facing an engineering challenge. We're facing the fundamental structure of space-time itself. The speed of light isn't just a speed limit for spaceships. It's a fundamental property of reality, built into the structure of space-time itself. According to Einstein's special relativity, as an object with mass accelerates closer to the speed of light, its mass effectively increases, requiring ever more energy to accelerate further. To actually reach the speed of light would require infinite energy, which isn't just impractical, but literally impossible. No matter what propulsion system we develop, no matter what energy source we harness, we cannot exceed this limit. And even if we could somehow reach 99.99% of the speed of light, a journey to Andromeda would still take 2.5 million years from the perspective of observers on Earth. Time dilation would help the travelers, making the journey shorter from their perspective, but they would still arrive to find Earth and everything they knew aged or destroyed by millions of years of history. Despite these crushing facts, what shadows might lurk in the equations of physics that could offer us escape routes from this prison? What if the universe has loopholes we haven't discovered yet? Or what if the very nature of space and distance isn't quite what we think it is? Let's talk about energy requirements, because even if we could somehow tolerate the journey times, the sheer amount of energy needed to accelerate a spacecraft to relativistic speeds creates another seemingly insurmountable barrier. The numbers here don't just stagger the imagination. They break it entirely. Consider a modest spacecraft, perhaps the size of the International Space Station, with a mass of about 420,000 kilograms. That's roughly 420 metric tons, not including fuel, which we'll get to in a moment. To accelerate this spacecraft to just 10% of the speed of light, you would need approximately 9 joules of energy. For comparison, total human energy consumption in 2023 was about 6 joules for the entire year. So accelerating one spacecraft to 1/10 light speed would require more energy than all of humanity currently produces in a year. Now remember, that only gets us to 10% light speed. At that velocity, reaching Andromeda would take 25 million years. Not exactly practical for a human mission. To make the journey in something resembling a reasonable time frame, say 10,000 years, we'd need to travel at 25% of light speed. The energy requirements scale with the square of velocity, meaning that 25% light speed requires roughly 6.25 times more energy than 10% light speed. We're now talking about using several years' worth of humanity's total energy output just to launch one spacecraft. But wait, it gets worse. Everything we've discussed so far assumes you can somehow convert energy into velocity with perfect efficiency, which is impossible. Real propulsion systems have to obey the rocket equation, which states that your final velocity depends on your exhaust velocity and the ratio of your initial mass to your final mass. In other words, you need to carry fuel, and that fuel has mass, which means you need more fuel to accelerate that mass, which adds more mass, requiring more fuel in an exponential relationship that quickly becomes absurd. Let's consider the most efficient propulsion system we currently understand, a perfect matter-antimatter annihilation drive. When matter and antimatter meet, they annihilate completely, converting 100% of their mass into energy according to Einstein's E equals mc. This is the most efficient energy conversion physically possible. Even with this perfect system, to accelerate our 420-ton spacecraft to 25% light speed, you would need approximately 8,000 tons of matter-antimatter fuel. But remember, that fuel also has mass that needs to be accelerated, which means you need more fuel, which has more mass, in a vicious cycle. When you work through the tyrannical mathematics of the rocket equation, you find that reaching even 10% of light speed with a matter-antimatter drive would require carrying fuel with a mass roughly equal to the payload. For higher speeds, the ratios become comically impossible. To reach 90% light speed, you'd need fuel masses hundreds or thousands of times greater than the payload, depending on your exhaust velocity and efficiency. And here's a delightful additional problem. Antimatter doesn't exist in any meaningful quantity in our universe. The total amount of antimatter ever created by humanity measures in nanograms. Creating a single gram of antimatter would cost roughly $62.50 trillion at current efficiency levels, and would require more energy than small countries use in a year. Creating thousands of tons of antimatter would require a Kardashev Type II civilization capable of harnessing the entire energy output of a star. Perhaps we could use fusion instead? A deuterium-tritium fusion reaction converts about 0.4% of the fuel mass into energy. That's far better than chemical rockets, which convert less than 0.0001% of fuel mass to kinetic energy, but still nowhere near the efficiency needed for relativistic travel. A fusion rocket could theoretically reach 10% light speed, but the engineering challenges of sustaining controlled fusion while using it as a rocket exhaust are staggering. We haven't even achieved net positive fusion energy on Earth yet, let alone weaponized it into a propulsion system that could operate continuously for decades or centuries. What about alternatives to rockets entirely? The concept of a laser sail has been proposed, a giant reflective sail pushed by powerful lasers from a solar system. The advantage is that the spacecraft doesn't need to carry fuel. The energy comes from outside. The Breakthrough Starshot Initiative plans to use this concept to send tiny probes to Alpha Centauri at 20% light speed. But scaling this up to a crewed spacecraft creates enormous problems. The laser array would need to be extraordinarily powerful, capable of delivering sustained petawatts of power. The sail would need to be enormous, potentially hundreds of kilometers across, yet impossibly thin and lightweight. And there's no way to slow down at the destination, unless the target system also has a laser array waiting, which obviously wouldn't exist for any intergalactic journey. The energy problem also manifests in subtler ways. At relativistic speeds, even individual hydrogen atoms in the interstellar medium become deadly radiation. A hydrogen atom hitting your spacecraft at 90% light speed strikes with the energy of a cosmic ray. The ESM has an average density of about 1 atom per cubic centimeter. At high relativistic speeds, you'd need massive shielding just to survive the wind of particles you're flying through. That shielding adds more mass, requiring more energy, creating another vicious cycle. Some proposals suggest using magnetic fields to deflect charged particles, but this requires enormous amounts of energy to maintain and doesn't help with neutral particles or photons. You're trading one energy problem for another, never quite escaping the tyranny of physics. But what if these numbers hide something more? What if there are ways to manipulate space-time itself rather than merely moving through it? Approaches that might bypass the rocket equation entirely. Here's where things get interesting, and where the scientific community starts dividing into camps. In 1994, a Mexican physicist named Miguel Alcubierre published a paper that sent ripples through the physics community. He proposed a mathematical solution to Einstein's field equations that would allow faster-than-light travel without actually violating relativity. The concept, now known as the Alcubierre drive or warp drive, doesn't move a spacecraft through space faster than light. Instead, it moves space itself, contracting space in front of the ship and expanding it behind, creating a warp bubble that carries the ship along with it. Think of it like surfing on a wave. The surfer isn't moving faster than water can flow. They're being carried by the wave itself. An Alcubierre drive would create a wave in spacetime, and the spacecraft would ride inside it. From the perspective of the ship, it's not moving at all. It's stationary inside its bubble, while space flows around it. From the perspective of outside observers, the ship appears to be moving faster than light, but it's not actually violating relativity because it's not moving through space. Space is moving. This isn't science fiction. The mathematics works. Alcubierre's solution is a valid solution to Einstein's field equations, meaning it's theoretically possible within our current understanding of physics. Scientists at NASA's EagleWorks laboratory have even investigated practical implementations, and physicist Harold "Sonny" White proposed modifications to the original design that would reduce the energy requirements from impossible to merely absurd. But here's where the anomaly becomes troubling. To create an Alcubierre drive, you need something called exotic matter with negative mass energy density. This isn't antimatter, which has positive mass. This is matter that has negative mass, something that effectively has less than zero energy. Such matter would have bizarre properties. It would fall upward in a gravitational field. It would accelerate when you pushed it away and decelerate when you pulled it toward you. It would violate every intuition we have about how objects behave. Does exotic matter exist? We don't know. We've never observed it. The closest thing we know of is the Casimir effect, a quantum phenomenon where two metal plates placed extremely close together in a vacuum experience an attractive force because the quantum vacuum between them has slightly less energy than the vacuum outside. Some physicists argue this demonstrates that negative energy density can exist under specific conditions. Others argue that while the Casimir effect involves negative energy compared to the surrounding vacuum, it doesn't involve truly negative mass energy density in the way the Alcubierre drive requires. The energy requirements for an Alcubierre drive, even with White's modifications, are staggering. The original calculation suggested you'd need a mass energy equivalent to Jupiter, or even the visible universe, converted entirely into exotic matter with negative mass. White's modifications reduced this to something closer to the mass of Voyager 1, about 700 kilograms, converted into exotic matter. That's still impossibly beyond our current capabilities, but it's at least a number that doesn't immediately break your calculator. There's another problem, possibly more fundamental. In 2012, physicists showed that an Alcubierre drive, if it could be created, would accumulate particles and radiation at its leading edge as it travels. When the drive is deactivated, this accumulated energy would be released in an intense burst that could destroy the destination. You'd essentially turn your spacecraft into a planet-destroying weapon every time you stopped. Other analyses suggest that an observer at the edge of the warp bubble would see the interior as infinitely blue-shifted, meaning they'd observe infinite energy density. The drive might collapse into a black hole before it could even function. These issues might be addressable with further modifications to the design, or they might represent fundamental barriers that make the Alcubierre drive impossible, even if exotic matter exists. The scientific debate continues, with papers published arguing both for and against various aspects of the concept. What makes this particularly intriguing is that Einstein's equations don't just permit the Alcubierre drive. They permit an entire zoo of exotic spacetime geometries, wormholes, closed time-like curves that allow time travel, and various other bizarre configurations. The equations themselves are surprisingly permissive. It's the energy conditions and requirements that seem to make these solutions physically unrealizable. Some physicists have proposed that there might be a cosmic censorship principle at work, a deeper law of physics we haven't yet discovered that forbids these exotic spacetime configurations from actually existing. The universe might allow them mathematically, but prohibit them physically, like how you can write down the equation for a square circle, even though such an object cannot exist. Others point out that our understanding of quantum mechanics and general relativity remains incomplete. We don't have a working theory of quantum gravity. At the scales and energy densities where quantum effects and gravitational effects become equally important, we simply don't know what the laws of physics are. It's possible that a complete theory of quantum gravity might reveal possibilities we haven't imagined, or it might close doors we thought were open. The Alcubierre drive represents something unprecedented in physics, a solution to our most trusted equations that would solve one of humanity's greatest challenges, but which requires resources and materials we're not sure can exist. It's tantalizing and frustrating in equal measure, like finding a locked door with a keyhole, but no key in sight. Recent work has explored other spacetime manipulation concepts. The warp drive concept has evolved into discussions of spacetime engineering, where civilizations might manipulate the metric of space itself in various ways. Some proposals suggest using rotating cylinders of dense matter to create frame-dragging effects that could be exploited for propulsion. Others explore whether quantum effects might be leveraged at macroscopic scales to create propulsion without propellant. All of these concepts share a common thread. They're trying to find loopholes in physics, ways to achieve what seems impossible within the constraints of known laws. They're not violating physics. They're looking for edge cases and special circumstances where the rules might permit something extraordinary. But here's what should give us pause. The universe has had 13.8 billion years to produce intelligent civilizations. If these loopholes exist and are accessible, why haven't we seen evidence of their use? Why isn't the galaxy teeming with intergalactic travelers? The apparent absence of alien civilizations, the Fermi paradox, might be telling us something important about these speculative technologies. Perhaps they truly are impossible. Perhaps the universe has drawn firm boundaries around each galaxy, and no amount of cleverness can cross them. This chemical signature of exotic matter, this theoretical possibility that sits at the edge of known physics, opens doors to speculation that becomes increasingly urgent as we contemplate humanity's long-term future. But before we venture too far down that road, we need to address the elephant in the room. What would actually happen if we tried to leave the galaxy with current technology? Let's directly address the worst-case physical scenario. What happens if we actually attempt intergalactic travel with current or near-future technology? Not speculative warp drives or exotic physics, but actual chemical or even fusion rockets, generation ships spanning centuries or millennia, the sort of thing that's merely extremely difficult rather than seemingly impossible. The answer is both mundane and horrifying. Nothing dramatic happens. There's no cosmic barrier that destroys the ship, no alien force that interdicts the journey. The ship simply travels for so long that everyone aboard dies, their descendants die, and their descendants' descendants die, through so many generations that the civilization aboard the ship would evolve beyond recognition, and still the journey would be barely begun. Let's run the numbers precisely. Imagine we build a generation ship using nuclear pulse propulsion, the Orion concept developed in the 1950s, where you literally throw nuclear bombs behind your spacecraft and surf the shockwave. This could theoretically reach 3 to 5% of light speed, making it one of the faster propulsion concepts we could actually build with current understanding of physics. At 5% of light speed, traveling to Andromeda would take 50 million years. 50 million years ago, Earth was in the Miocene epoch. Primates existed, but were nothing like humans. The entire evolutionary line from early primates to Homo sapiens would span less time than this single journey. The ship would need to be completely self-sustaining, a sealed ecosystem capable of recycling everything indefinitely. Any failure in any system, air recycling, water purification, food production, waste management, would be catastrophic and permanent. The biological challenges are equally severe. Over 50 million years, with a necessarily small founding population, genetic drift would be extreme. The population aboard would need to be large enough to maintain genetic diversity, probably at least several thousand individuals, but small enough that the ship's resources can support them indefinitely. They'd need to carefully manage reproduction rates to prevent population explosions or collapses. They'd be creating a new evolutionary environment where selection pressures would be completely different from Earth, likely resulting in speciation. The beings that arrived at Andromeda wouldn't be human in any meaningful sense. The psychological and sociological challenges might be even worse. How do you maintain cultural continuity across millions of years? How do you preserve the mission's purpose when the destination is so distant that it's mythological rather than real to the people aboard? Early generations might maintain the vision, but after hundreds of thousands of generations, the ship itself becomes the universe to its inhabitants. The destination becomes a religious concept rather than a place, and the mission might be abandoned or forgotten entirely. The ship would also face continuous erosion. Cosmic rays would slowly damage materials. Micrometeorite impacts, even with shielding, would accumulate over such time scales. Systems would fail and need replacement, requiring manufacturing capabilities aboard the ship. You're not just launching a spacecraft. You're launching an entire industrial civilization, complete with mines, factories, and universities, all inside a hull traveling through the void. There's also the problem of navigation and communication. At 5% light speed, you're still traveling slow enough that you'd need to actively navigate around obstacles. The interstellar medium isn't empty. There are molecular clouds, dust lanes, and other hazards. But you're traveling fast enough that light-speed communication with Earth becomes meaningless. A message would take millions of years to arrive, and any response would take millions more. The ship would be utterly on its own, unable to receive help or updated instructions, facing whatever challenges arise with only their onboard resources. The energy requirements for maintaining all these systems over such timescales are staggering. Even with fusion power, which we still haven't achieved, you'd need enough fuel to power an entire civilization for millions of years. The mass of that fuel alone would be enormous, requiring more energy to accelerate, creating the same vicious cycle we discussed earlier. And here's perhaps the most depressing aspect, the uncertainty about the destination. We can't study Andromeda in enough detail to know if it even has habitable worlds. We can barely detect planets around nearby stars in the Milky Way. Detecting planets in another galaxy is currently impossible. The generation ship would be traveling to a destination they can't verify is worth reaching, gambling everything on statistical probabilities about planet formation and habitability. Now, some might argue we could use suspended animation or cryogenic freezing to preserve the original crew. Setting aside the fact that we can't currently do this with humans, there's a deeper problem. Systems designed to keep people frozen would need to function perfectly for millions of years. Any failure means death. The ship would still need to be maintained, requiring either AI systems sophisticated enough to handle any possible problem, or rotating crews that defeat the entire purpose of cryosleep. The brutal truth is that with current physics and plausible near-future technology, intergalactic travel isn't just impractical. It's effectively impossible for biological beings. The timescales are simply too long, the distance is too vast, the resource requirements too extreme. Even if we solve every engineering challenge, even if we build generation ships that could theoretically sustain life for millions of years, the chances of success approach zero. This bears repeating. The physical threat of intergalactic travel isn't that something will destroy the ship. It's that time itself is the destroyer. Entropy, the slow degradation of all systems, becomes an insurmountable enemy. Over millions of years, everything breaks down, every system fails, every carefully planned redundancy eventually exhausts itself. So when we talk about the worst case for intergalactic travel with known physics, it's not a dramatic explosion or a cosmic catastrophe. It's a slow, grinding failure that plays out over timescales, so long they become meaningless to human psychology. It's the universe saying, not with violence, but with patience, that some distances cannot be crossed, that some boundaries cannot be breached. But what if the real worst case has nothing to do with physical danger, or even the impossibility of the journey itself? What if there's something more subtle and more troubling at work, something that suggests our confinement to the Milky Way might not be an accident of physics, but a feature of cosmic architecture? Let's venture into speculative territory here, clearly labeled as such, because there's a darker possibility that some scientists take seriously. What if the inability to leave one's home galaxy isn't a bug in the universe's design, but a feature? What if the vast distances between galaxies serve a purpose cosmic quarantine that prevents civilizations from spreading too far, too fast, or from making contact with each other until they reach certain levels of technological or ethical development? This idea connects to one of the most troubling concepts in astrobiology, the Great Filter. Proposed by economist Robin Hanson in 1996, the Great Filter hypothesis attempts to explain the Fermi paradox. Why, in a universe with billions of galaxies, each containing billions of stars, we see no evidence of alien civilizations, despite having the capability to detect signs of their existence? The Great Filter suggests there's some evolutionary step, some threshold, that's extraordinarily difficult for life to pass through. It could be behind us, perhaps the origin of life itself is so improbable that Earth might be the only planet where it occurred. Or it could be ahead of us, perhaps. Civilizations inevitably destroy themselves before achieving interstellar travel. Or they face some other insurmountable challenge that prevents them from becoming visible on galactic scales. But here's the speculative leap. What if intergalactic distances themselves are the Great Filter? Not for life's origin, or even for spacefaring civilizations, but for the spread of civilizations beyond their home galaxies? This would be a soft filter rather than an extinction-level event. Civilizations could arise, flourish, spread throughout their home galaxies, survive for millions or billions of years, and still never escape their galactic confines. The universe would be full of life, full of civilizations, but each one trapped in its island universe, looking out at countless other islands they can never reach. Some scientists, including physicist Paul Davies, have speculated about this possibility. If the universe is teeming with life, but intergalactic travel is genuinely impossible even for arbitrarily advanced civilizations, and each galaxy becomes a separate evolutionary experiment. Life on Earth would never encounter alien life from other galaxies, not because it doesn't exist, but because the distances are an impassable barrier, even for species millions of years more advanced than us. This would solve certain versions of the Fermi paradox. We don't see galactic-scale civilizations in other galaxies because they can't escape their home galaxies any more than we can. The various explanations for why advanced civilizations might not be visible. Perhaps they transcend physical existence. Perhaps they hide deliberately. Perhaps they destroy themselves. Wouldn't be necessary. They simply can't reach us, and we can't reach them, separated by gulfs of space and time that even technological civilizations, millions of years old, cannot bridge. Now, let me emphasize, this is speculation. There's no evidence supporting this beyond the fact that intergalactic distances are enormous and the physics is challenging. But it's speculation that some serious scientists find worth considering, because it would explain several puzzling observations. First, it would explain why SETI has found nothing despite decades of searching. If civilizations are confined to their galaxies, and if there are few or no other civilizations in the Milky Way, which itself needs explanation, then we wouldn't expect to detect signals. The nearest civilizations might be in Andromeda or other nearby galaxies, transmitting signals we can't detect because they're too distant, or because they've passed through our region of space long ago or will arrive long after we're gone. Second, it would explain the apparent great silence despite the age of the universe. The universe is 13.8 billion years old. Galaxies like the Milky Way have been capable of supporting life for roughly 10 billion years. If life is common, there should have been billions of years for civilizations to arise, spread, and become visible. The fact that we see no evidence of galaxy-spanning civilizations anywhere in the observable universe is genuinely puzzling, unless there's something preventing civilizations from reaching that scale, or unless they do reach it, but remain confined to their home galaxies, where we can't detect them from our position in the Milky Way. Third, and most provocatively, it would suggest that the universe has a built-in safety mechanism. If civilizations are naturally confined to their galaxies, they can't threaten each other across intergalactic distances. A malevolent civilization, no matter how advanced, can't spread beyond its galaxy to threaten others. A civilization that develops dangerous self-replicating technology can't contaminate the entire universe, only its local galactic neighborhood. The cosmic quarantine protects the universe from the worst outcomes of intelligent life. Some physicists have gone further, suggesting that the laws of physics themselves might be fine-tuned to create this quarantine effect. The speed of light, the expansion rate of the universe, the distribution of matter, all of these could theoretically have been different. Perhaps the universe we inhabit is specifically structured to allow life to arise and flourish within galaxies, while preventing life from spreading between galaxies. This edges into anthropic principle territory, the controversial idea that the universe's properties are what they are, because if they were different, we wouldn't be here to observe them. Carl Sagan explored similar ideas, suggesting that the galaxy might be divided into trade routes and wilderness, regions where civilizations can meet and interact, and vast deserts between them where nothing can survive the journey. If true, we might live in one of the wilderness regions, far from any trade routes, effectively isolated by our cosmic geography. Others, like physicist Enrico Fermi himself, for whom the paradox is named, wondered if advanced civilizations might voluntarily limit their expansion. Perhaps there's a universal ethical consensus that spreading too widely causes problems, or perhaps the resources required for expansion become prohibitive at certain scales. Intergalactic distances might represent a natural boundary where even if civilizations could expand further, they choose not to because the cost-benefit ratio becomes unfavorable. But these are all speculations built on speculations. We have exactly one data point: ourselves. We're a young civilization that has barely left its home planet, let alone its solar system or galaxy. Making grand conclusions about the nature of the universe and the fate of all civilizations, based on our limited perspective, is presumptuous at best. Yet the speculation persists because the alternative is almost as troubling. If intergalactic distances aren't a universal barrier, if sufficiently advanced civilizations can overcome them, then why don't we see evidence of such civilizations? Where are the galaxy-spanning empires? Where are the Kardashev Type 3 civilizations harnessing the energy output of entire galaxies? Where are the signs of cosmic engineering on galactic scales? The silence might mean we're alone, which is terrifying. Or it might mean we're early, among the first civilizations to arise, which is improbable given the age of the universe. Or it might mean that something prevents civilizations from reaching such scales, whether that's self-destruction, transcendence beyond the physical universe, or cosmic quarantine through insurmountable distances. This speculation about cosmic imprisonment takes us to darker territory still, because if the distances are genuinely impassable, if we're locked in the Milky Way for all time, what does that mean for humanity's ultimate fate? Now, let's venture deep into the most dramatic what-if territory, with constant reminders that this is speculation built on incomplete knowledge. But it's speculation worth exploring because it touches on fundamental questions about humanity's place in the cosmos and our ultimate destiny. What if we're not just confined to the Milky Way by physics, but we're also alone in it? What if the combination of cosmic quarantine between galaxies and the rarity of life within galaxies means that humanity is the only conscious intelligence in our cosmic neighborhood, and potentially the only intelligence we'll ever have the opportunity to encounter? This is the rare Earth hypothesis taken to its logical extreme. The idea, proposed by Peter Ward and Donald Brownlee, suggests that while simple microbial life might be common in the universe, complex multicellular life, and especially intelligent life, might be extraordinarily rare due to the number of unlikely factors that must align. Earth's large moon stabilizing its axial tilt, Jupiter's gravitational influence deflecting asteroids, our position in the galactic habitable zone, our star's stability and longevity, the presence of plate tectonics to recycle carbon, and dozens of other factors all had to come together. If the rare Earth hypothesis is correct, and if intergalactic distances are truly impassable, then we face a scenario of cosmic loneliness that's difficult to fully comprehend. The Milky Way contains somewhere between 200 and 400 billion stars. But if only 1 in a billion of those stars hosts intelligent life, and if we're separated from any other intelligence by thousands or tens of thousands of light years, we might never make contact even within our own galaxy. This creates a particular kind of existential crisis. Humanity would be, for all practical purposes, alone in a universe containing trillions of galaxies and septillions of stars. Not alone in the absolute sense. Perhaps there are millions of other civilizations out there, but alone in the functional sense that we can never reach them, never learn from them, never share our art and science and philosophy with them, never know if our struggles and triumphs have any cosmic significance. The psychological implications are profound. Much of human culture is built on the idea of connection, legacy, and meaning derived from our relationships with others. What does it mean for a species to recognize that it might be effectively alone for the entire span of its existence? That every achievement, every work of art, every scientific discovery, every moral advancement we make will be witnessed only by our descendants, never by other minds that evolved independently under alien stars? Some philosophers and scientists argue this would be liberating. If we're alone, we have no competition, no threat from hostile aliens, no risk of being outcompeted or destroyed by more advanced civilizations. The galaxy would be ours to explore and settle at our leisure, limited only by our own capabilities and choices. We would be the authors of our own destiny, without external constraints or interference. But there's a darker interpretation. If we're alone and confined to the Milky Way, then the ultimate fate of consciousness in our region of the universe rests entirely on our shoulders. If humanity fails through nuclear war, climate catastrophe, artificial intelligence gone wrong, or any of the other existential risks we face, there might be no one else to carry the torch of intelligence forward. The universe would continue for trillions of years. Stars would be born and die. Planets would form and be destroyed. But there would be no one to witness it, no one to understand it, no one to marvel at its beauty or unravel its mysteries. This is what physicist John Wheeler called the participatory universe, the idea that consciousness plays a crucial role in making the universe real in some sense. Without observers, quantum mechanics suggests the universe exists in a superposition of all possible states. Consciousness collapses those wave functions, making reality definite. If Wheeler is even partially correct, the extinction of consciousness in our galaxy would represent not just a tragedy, but a kind of cosmic catastrophe, a region of spacetime that returns to mere probability rather than actuality. Now let's go even further into speculative territory. What if the cosmic quarantine isn't just about distance? What if there's something more deliberate at work? Some scientists have proposed that we might live in a simulation, a computational universe created by some higher-level intelligence. If true, the inability to leave the Milky Way might be a deliberate design constraint, a way of limiting the computational resources required to simulate our region of reality. Or consider the zoo hypothesis, the idea that alien civilizations know about us but deliberately avoid contact, treating Earth like a nature preserve or an anthropological study. If combined with cosmic quarantine, this would suggest that each galaxy is a separate zoo, with civilizations inside unable to leave and civilizations outside unable or unwilling to enter. These scenarios start to sound like science fiction, and indeed, they've inspired countless stories, from Arthur C. Clarke's explorations of cosmic loneliness to Greg Egan's investigations of simulated realities. But they emerge from genuine attempts to reconcile the Fermi paradox with our observations of the universe. The absence of evidence for alien civilizations demands explanation, and some of those explanations lead to unsettling conclusions. There's also the temporal dimension to consider. Even if other civilizations exist in the Milky Way, the galaxy is so old, and stars have such long lifetimes that civilizations might arise millions or billions of years apart. We could be separated from our nearest neighbors, not just by space, but by time. Previous civilizations might have risen and fallen billions of years ago, leaving no trace we can detect. Future civilizations might not arise until long after our sun has died. This temporal isolation, combined with spatial isolation, creates a universe where consciousness is scattered across space and time like sparse, brief flashes of light in an otherwise dark void. Each flash burns for a few million years, a cosmic eye blink, and then fades, perhaps never overlapping with any other flash closely enough in space and time for meaningful interaction. If this is our reality, it means that despite the vastness of the universe and the abundance of stars and planets, intelligent life might be functionally isolated on scales that matter for experience and interaction. The universe would be simultaneously full of life and empty of company, populated but lonely, teeming with consciousness that never connects. Some find this scenario deeply depressing. Others find it motivating, arguing that it makes our survival and flourishing even more important. If we're one of the few islands of consciousness in a vast ocean of unconscious matter, then our responsibility to preserve and expand that consciousness becomes paramount. Every human life, every thought, every creative act becomes cosmically significant because there might be so few of them in the universe. The worst-case speculative scenario, then, isn't about physical danger or technological failure. It's about meaning and connection. It's about the possibility that we're shouting into a void that either contains no one else or contains others who are also shouting but can never hear us. It's about the recognition that the universe's architecture might ensure that consciousness, wherever it arises, remains isolated and alone, unable to bridge the vast distances that separate it from other minds. This is speculation, remember. We have no evidence that we're alone in the galaxy, let alone alone in any meaningful sense. The search for extraterrestrial intelligence continues, and every year we discover more exoplanets, more potentially habitable worlds, more reasons to think that life might be common. But the speculation is worth exploring because it forces us to confront the implications of cosmic isolation, whether that isolation is absolute or merely practical. If we can't leave the Milky Way, if the barriers are truly impassable, even for civilizations millions of years more advanced than us, then our cosmic neighborhood becomes our cosmic horizon. Everything beyond it becomes, in a sense, fictional, visible but untouchable, existing but irrelevant to our lived experience and our ultimate destiny. But this raises profound questions about how we would respond to such knowledge, how our institutions and our species would adapt to the recognition that we're confined to one galaxy for all time. What would that do to human civilization and our sense of purpose? To understand why intergalactic isolation might matter so profoundly, we need to explore the broader context of the Fermi paradox and the questions it raises about intelligence, technology, and cosmic destiny. This isn't just about whether we can leave the Milky Way. It's about what it means if we can't, and what it tells us about the universe we inhabit. The Fermi paradox, named after physicist Enrico Fermi's casual lunchtime question, "Where is everybody?" has become one of the most productive thought experiments in science. It starts with a simple observation. The universe is very old and very large. The Milky Way alone has existed for over 13 billion years. If intelligent life is common, even one other civilization should have had time to spread throughout the galaxy multiple times over. Consider the timescales involved. Our solar system formed 4.6 billion years ago. Life appeared on Earth within the first billion years. Multicellular life took another 3 billion years. Humans emerged in the last few million years, and technological civilization in the last few thousand. This entire history, from sterile rock to spacefaring species, took less than 5 billion years. Now imagine a civilization that started just 1 million years before us, a tiny margin in cosmic terms. With even modest technology, spreading throughout the galaxy at sublight speeds, they would have colonized every star system long before Earth even formed. We should see evidence of them everywhere. Megastructures around stars, radio signals, artifacts in our own solar system, terraformed worlds, Dyson spheres harvesting stellar energy. We see none of that. The galaxy appears silent, empty, pristine. This is the heart of the Fermi paradox, and it demands explanation. Dozens of proposed solutions exist, ranging from the mundane to the exotic. Perhaps life is rare, the rare Earth hypothesis. Perhaps intelligence is rare, even when life is common. Perhaps civilizations inevitably destroy themselves before achieving interstellar travel, through nuclear war, environmental collapse, or other catastrophes. Perhaps advanced civilizations transcend physical existence, uploading themselves into computational substrates or ascending to higher dimensions we can't perceive. Or perhaps, and this is where intergalactic distances become relevant, perhaps the universe's structure naturally prevents civilizations from becoming visible on galactic scales, not because they destroy themselves, but because the physics of expansion and travel creates natural boundaries that even million-year-old civilizations cannot easily cross. This connects to an idea called the Kardashev scale, proposed by Soviet astronomer Nikolai Kardashev in 1964. It categorizes civilizations by their energy consumption. Type I harnesses all the energy available on its home planet. Type II harnesses all the energy of its star, perhaps through a Dyson sphere. And Type III harnesses all the energy of its galaxy. Humanity currently rates about 0.73 on this scale. We're not even Type I yet. If intergalactic distances are truly impassable, then type 3 might represent an absolute ceiling. No civilization, regardless of its age or advancement, could progress beyond type 3 because the energy required to spread beyond its home galaxy is prohibitive or the timescales are too long. Each galaxy becomes a separate domain, hosting civilizations that might reach type 3 but can never interact with type 3 civilizations in other galaxies. This would create a universe that's simultaneously full of advanced civilizations and empty of galaxy-spanning super-civilizations. It would explain why we don't see evidence of Kardashev type 3 civilizations when we look at other galaxies. They exist, but they're confined to their galaxies, just as we're confined to ours. The implications extend to something called the Great Filter, which we touched on earlier. The Great Filter hypothesis suggests that there's at least one step in the evolution from sterile planet to galaxy-spanning civilization that's extremely improbable. The question is whether that filter is behind us or ahead of us. If it's behind us, if the hard step is the origin of life, or the evolution of eukaryotic cells, or the development of intelligence, then we might be among the first civilizations to arise, or possibly even alone in the galaxy. This would be simultaneously wonderful, we're special, and terrifying. The responsibility for consciousness in our region of space rests entirely on us. If the Great Filter is ahead of us, that's more ominous. It would suggest that something prevents civilizations from reaching the level where they become visible on galactic scales. Perhaps nuclear weapons make self-destruction inevitable. Perhaps artificial intelligence inevitably surpasses biological intelligence, and either destroys its creators or chooses not to expand. Perhaps there's some other technological threshold that civilizations typically don't survive crossing. But if intergalactic distances represent a soft, Great Filter, not an extinction event, but a natural boundary, then the filter might be neither behind us nor ahead of us in the sense of representing a threat. Instead, it's simply a feature of cosmic geography. Civilizations can arise, flourish, spread throughout their galaxies, and survive for millions of years. They just can't spread beyond their galactic boundaries. This would actually be somewhat comforting. It means the universe isn't necessarily hostile to advanced civilizations, and technological progress doesn't necessarily lead to self-destruction. It just means the playground is smaller than we might have hoped, limited to a mere 100,000 light-years rather than 46.5 billion light-years. The physicist Frank Drake created an equation attempting to estimate the number of communicative civilizations in the Milky Way. Drake equation multiplies together factors like the rate of star formation, the fraction of stars with planets, the number of habitable planets per star system, the fraction where life actually arises, the fraction where life develops intelligence, the fraction where intelligence develops detectable technology, and the length of time such civilizations remain detectable. The equation is less about getting a precise number and more about organizing our uncertainty. We know some of these factors reasonably well, star formation rates, for instance, but others are pure guesses. How common is abiogenesis, the origin of life from non-life? We have exactly one example: Earth. How common is the evolution of intelligence? Again, one example, though we can look at the evolution of intelligence in dolphins, octopi, and other Earth species for hints. When Drake originally proposed the equation in 1961, he estimated there might be thousands or tens of thousands of communicative civilizations in the Milky Way. More pessimistic estimates suggest fewer than one, meaning we might be alone. More optimistic estimates suggest millions. The range of uncertainty is enormous, and after decades of searching with SETI, we still have no confirmed detections. This uncertainty about life's prevalence combines with the certainty about intergalactic distances to create a situation where humanity might be confined to the Milky Way, regardless of whether we're alone in it or sharing it with thousands of other species. The cosmic isolation might be physical rather than biological, which leads to questions about how we would respond to such knowledge. Let's explore an even deeper philosophical question that emerges from our discussion of cosmic boundaries. Why is the universe structured this way? Why are the distances so vast, the speed of light so limiting, the energy requirements so extreme? Is there something about the fundamental constants of nature that necessarily creates this cosmic isolation? And if so, what does that tell us about the universe we inhabit? This leads us into territory called the anthropic principle, one of the most controversial concepts in modern physics and cosmology. At its simplest, the weak anthropic principle states that we observe the universe to have properties that allow our existence, because if it didn't have those properties, we wouldn't be here to observe it. This is almost tautological. Of course, we find ourselves in a universe capable of supporting observers. But the strong anthropic principle goes further, suggesting that the universe must have properties that allow consciousness to develop at some point in its history. This edges toward teleology, the idea that the universe has purpose or direction, which makes many scientists uncomfortable. It sounds suspiciously like intelligent design or cosmic planning. Yet there's something genuinely puzzling about the constants of nature. The speed of light, Planck's constant, the gravitational constant, the masses of fundamental particles. These values appear to be finely tuned to allow for the existence of stars, planets, chemistry, and ultimately life. Change any of them by small amounts, and you get a universe that's either empty or so radically different that consciousness couldn't arise. For example, if the strong nuclear force were slightly weaker, atomic nuclei couldn't form, and there would be no atoms heavier than hydrogen. If it were slightly stronger, stars would burn out too quickly for life to evolve. If the electromagnetic force were different, chemical bonds wouldn't work the way they do, making complex molecules impossible. The list goes on. There are roughly 20 to 30 fundamental constants that seem to require very specific values for our universe to be possible. Now, here's where this connects to intergalactic isolation. The speed of light is one of these fundamental constants. It's not just a speed limit for matter. It's woven into the structure of space-time itself, appearing in Einstein's equations as a fundamental constant that relates space and time. If the speed of light were significantly faster, the universe would be very different. Time dilation effects would work differently. The relationship between energy and mass would change. Causality itself might break down. So perhaps the speed of light has to be roughly what it is for the universe to support life at all. And that necessarily creates vast cosmic distances that consciousness cannot easily bridge. The same fundamental physics that allows stars to shine and planets to form also ensures that galaxies remain isolated from each other. The cosmic quarantine isn't designed. It's emergent from the basic structure of reality. Some physicists have proposed the multiverse as a solution to fine-tuning. If there are countless universes with different physical constants, and we only observe the one where the constants allow observers to exist, then the apparent fine-tuning is just selection bias. We're in a Goldilocks universe, not because someone tuned it, but because the non-Goldilocks universes don't have anyone asking questions about fine-tuning. If the multiverse is real, there might be other universes where the speed of light is much faster, where intergalactic travel is trivial, where civilizations spread across cosmic superclusters with ease. But those universes might not have chemistry as we know it, or stable stars, or any of the other prerequisites for life. The universe that permits life might necessarily be the universe that isolates that life within galactic boundaries. This is deeply speculative, of course. We have no direct evidence for other universes, and some argue the multiverse idea isn't even scientific because it makes no testable predictions. But it provides a framework for understanding why our universe has the properties it does, including properties that make intergalactic travel so prohibitively difficult. There's another interpretation worth considering, one that's perhaps even more philosophical. What if consciousness itself requires boundaries? What if the experience of being a finite observer in an infinite universe requires limitations on what that observer can reach and know? Without boundaries, without horizons beyond which we cannot travel, Would existence have the same structure and meaning? This ventures into phenomenology and existential philosophy, domains where science blurs into metaphysics. But the question is genuine. Does meaning require limitation? Does the value of exploration require the existence of unexplorable regions? Does the excitement of discovery require the existence of undiscoverable truths? Humanity has always defined itself against frontiers. We've crossed oceans, climbed mountains, explored poles, and ventured into space. Each frontier, once crossed, ceased to be a frontier and became merely geography. But intergalactic space might represent a permanent frontier, a horizon that remains horizon no matter how far we advance technologically. How would that affect human psychology and culture? Some argue it'd be stifling, limiting human potential and ambition. Others suggest it would be focusing, concentrating our efforts on making the most of the cosmic territory available to us, rather than constantly pushing outward. The galaxy contains 200 to 400 billion stars. Even if only a tiny fraction of them could support human habitation, we're talking about millions or billions of potential worlds. That's hardly a small playground. The anthropic principle suggests we shouldn't be surprised to find ourselves in a universe with these properties, because only universes with these properties could produce observers to be surprised. But that doesn't necessarily make it less frustrating. We're like prisoners who understand the thermodynamic and structural reasons why our cell was built the way it was, but who still long for freedom beyond its walls. Yet there's a kind of cosmic democracy in this isolation. If intergalactic distances are impassable for everyone, then no civilization can dominate the universe. No empire can spread beyond its galaxy to threaten or conquer others. Each galaxy becomes a separate domain, autonomous and independent. The universe has, in a sense, built-in political boundaries that even the most aggressive civilizations cannot cross. This connects to ideas about cosmic sustainability. Resources within a galaxy are vast but finite. If civilizations can't escape their galaxies, they must eventually reach some form of equilibrium with their available resources. They can't endlessly expand, consuming new star systems and leaving dead husks behind. They must either develop sustainable relationships with their environment or face collapse. The cosmic boundaries enforce a kind of long-term thinking that unconstrained expansion wouldn't require. Perhaps most intriguingly, if each galaxy is isolated, then each one becomes an independent experiment in the evolution of intelligence and civilization. Life might arise on countless worlds, intelligence might develop countless times, and civilizations might explore countless different trajectories, all without interfering with each other. The universe becomes a vast laboratory with trillions of separate experiments running simultaneously, each isolated from the others. When we look at it this way, cosmic isolation isn't a prison. It's a protective barrier. It's what allows diversity to flourish without being homogenized by the first civilization to develop interstellar or intergalactic travel. It ensures that the universe remains filled with variety rather than becoming dominated by a single expanding empire. But these philosophical consolations don't change the practical reality. If we want to reach other galaxies, if we want to explore beyond the Milky Way, if we want to meet civilizations that evolved under alien suns in distant island universes, we face barriers that might be truly insurmountable. And that raises urgent questions about how we would respond if this speculation were confirmed as fact. Let's engage in a thought experiment that's part sociology, part psychology, part policy analysis. If humanity definitively confirmed that leaving the Milky Way is impossible, not just difficult with current technology, but physically impossible even for arbitrarily advanced civilizations, how would we respond? What would this do to our institutions, our culture, our sense of purpose and identity? First, consider the scientific response. The confirmation would likely come from advances in theoretical physics, perhaps a complete theory of quantum gravity that definitively rules out exotic space-time manipulations like Alcubierre drives and wormholes. Or it might come from practical demonstrations that certain physical limits cannot be exceeded, no matter what technology is developed. The scientific community would need to pivot from viewing intergalactic travel as a distant possibility to viewing it as a fundamental impossibility. This would redirect enormous research efforts. Instead of studying potential propulsion systems for intergalactic voyages, resources would shift toward maximizing what we can achieve within the Milky Way. How can we spread throughout our galaxy most effectively? How can we sustain civilization over the millions of years required for galactic colonization? How can we detect and potentially communicate with other civilizations within our galaxy? This wouldn't be a small shift. Significant research funding in physics and engineering currently focuses on exotic propulsion concepts, from fusion drives to antimatter engines to speculative ideas like Alcubierre drives. Confirming that intergalactic travel is impossible would make some of this research obsolete while elevating other approaches. The focus would shift from how do we go faster to how do we survive longer, and how do we make the most of our galactic neighborhood. Institutionally, space agencies would need to revise their long-term planning. NASA, ESA, CNSA, and other agencies currently operate with implicit assumptions about humanity's ultimate expansion into the cosmos. Many long-range plans and philosophical documents discuss humanity becoming a multiplanetary species, then an interstellar species, and eventually a galactic or even intergalactic species. Removing that final step would require rethinking what success looks like for spacefaring civilization. This might actually clarify certain strategic priorities. If the ultimate goal is spreading throughout the Milky Way rather than the universe, then we can optimize for that specific target. Generation ships don't need to function for millions of years to reach other galaxies. They only need to function for tens of thousands of years to reach distant star systems within our galaxy. That's still extraordinarily challenging, but it's a different kind of challenge with different design requirements. Politically and philosophically, the response would likely be mixed. Some groups would find cosmic isolation depressing, a limitation on human potential and destiny. Science fiction has conditioned many people to expect a future where humanity spreads across galaxies, meets countless alien civilizations, and plays a role on a cosmic stage. Learning that the stage is limited to one galaxy might feel like a loss of possibility and purpose. Others might find it liberating. Without the threat of alien civilizations from other galaxies, without the pressure to expand infinitely, humanity could focus on developing sustainably within our cosmic territory. We could take our time, make mistakes, and learn from them, without worrying about being outcompeted or overtaken by some exponentially expanding alien civilization from Andromeda. There would likely be religious and spiritual responses as well. Some traditions view humanity as having a special cosmic destiny or purpose. Learning that we're confined to one galaxy might be interpreted as divine will, cosmic design, or natural law, depending on one's perspective. Others might see it as a test or challenge, an opportunity to demonstrate what we can achieve within our limitations. Cultural responses would vary by society and demographic. Younger generations growing up with the knowledge that intergalactic travel is impossible might not feel the same sense of loss that older generations would experience. It's difficult to mourn the loss of something you never expected to have. Over time, the Milky Way would come to be seen not as a prison, but simply as home, the natural and expected scope of human civilization. Science fiction and popular culture would need to adjust. Countless stories rely on faster-than-light travel, intergalactic empires, and meetings between civilizations from different galaxies. If physics definitively rules out these possibilities, storytellers would need to work within new constraints or explicitly label their work as fantasy rather than science fiction. This could actually be creatively productive, pushing writers to explore scenarios that are more physically plausible while still capturing the sense of wonder and exploration that makes space opera appealing. Educational systems would need to update their presentations of humanity's cosmic future. Current science education often presents an implicit narrative of ever-expanding frontiers, from exploring Earth, to exploring the solar system, to exploring the galaxy, to eventually exploring the universe. If intergalactic travel is impossible, that narrative needs revision. Students would learn about the vastness and richness of the Milky Way rather than the vastness of the observable universe as humanity's domain. There might also be economic implications. Private space companies like SpaceX, Blue Origin, and others operate with long-term visions of human expansion into space. If intergalactic travel is impossible, does that affect the business case for space development? Probably not in the near term. There's more than enough opportunity within the solar system and potentially within nearby star systems to justify massive investment. But it might affect the rhetoric and vision that motivates investors and employees. From an existential risk perspective, knowing that we're confined to the Milky Way might actually increase the perceived urgency of certain challenges. If we can't escape to other galaxies as a backup plan, then ensuring the survival and flourishing of humanity within our galaxy becomes even more critical. Asteroid impacts, nuclear war, climate change, artificial intelligence risks, all of these take on added significance if we know we have no cosmic escape hatch. Paradoxically, confirmation of cosmic isolation might make humanity more ambitious about galactic expansion. If we know we can never leave the Milky Way, we might feel more urgency to at least fully explore and settle within it. The galaxy becomes our entire future, our complete cosmic inheritance, and we'd want to make the most of it. This could accelerate timelines for interstellar missions and increase investment in technologies that would make intragalactic travel more feasible. There would also be implications for how we think about the Fermi paradox and the search for extraterrestrial intelligence. If intergalactic travel is impossible, then we should only expect to potentially encounter civilizations from within the Milky Way. This narrows the search space significantly and might make SETI efforts more focused. We wouldn't need to worry about signals from other galaxies. We could concentrate entirely on our own. At the same time, it would make the continued silence of SETI more puzzling. If civilizations are confined to their galaxies, and if the Milky Way is old enough for civilizations to have arisen and spread, why don't we detect them? Are we alone even within our galaxy? Are we early? Are civilizations common but deliberately quiet? The great filter question becomes even more pressing when limited to galactic scales. Some philosophers have argued that accepting cosmic limitations is a form of wisdom, a recognition that not everything is possible or desirable. Just as individuals must accept the limitations of mortality, mortality of ability, and finitude of experience, humanity as a species might need to accept that there are cosmic boundaries beyond which we cannot travel. This acceptance doesn't mean giving up on exploration or ambition. It means channeling those impulses in directions that are actually achievable. The response would ultimately depend on how the impossible is confirmed and communicated. A gradual scientific consensus building over decades would allow for slow adaptation. A sudden, definitive proof might cause more disruption and require more active management of public expectations and reactions. But humanity has proven adaptable to discovering uncomfortable truths about our place in the universe before, that Earth isn't the center, that the solar system isn't the center, that the galaxy isn't the center. We could likely adapt to learning that our cosmic reach has hard limits too. The question becomes not whether we could adapt, but what that adaptation would look like, and whether it would ultimately be healthy for our species, long-term development, and sense of purpose. One of the most fascinating aspects of the intergalactic travel question involves how we balance the human drive for knowledge with the practical implications of that knowledge. If research definitively showed that leaving the Milky Way is impossible, should that information be widely shared? Or would there be arguments for limiting its dissemination, at least initially? This isn't about conspiracy or cover-up in the popular sense. It's about responsible information management when dealing with potentially civilization-altering revelations. Scientists and policymakers have grappled with similar questions before. Should research on dangerous pathogens be published openly? Should details of nuclear weapon design be freely available? Should AI safety research be conducted transparently or behind closed doors? The argument for openness is straightforward. Humanity benefits from shared knowledge. Scientific progress requires transparency, peer review, and broad participation. Keeping cosmic limitations secret would require impossible levels of coordination across international boundaries and academic institutions. Moreover, people have a right to know fundamental truths about their universe and their place in it. History strongly favors transparency. Every attempt to suppress scientific knowledge has eventually failed and often backfired. The Catholic Church's response to Galileo didn't stop heliocentrism. It just damaged the Church's credibility. Soviet censorship of genetics didn't change the facts of evolution. It just held Soviet biology back for decades. You can't make the universe different by refusing to acknowledge what it is. But there are counter-arguments worth considering, even if ultimately we reject them. Some psychologists have suggested that confirmation of cosmic isolation could negatively affect human motivation and mental health. If people believe the universe is fundamentally closed to them, might they become more fatalistic, more focused on short-term gratification rather than long-term building? Would it increase nihilism or decrease the sense of cosmic purpose that drives some people? These concerns probably give too little credit to human resilience and adaptability. People find meaning and purpose in bounded systems all the time. The fact that we can't live forever doesn't make most people suicidal. It makes many people more intentional about how they use their time. The fact that we can't visit the past doesn't make history meaningless. Limitation and finitude are part of the human condition at every scale. Moreover, the Milky Way is hardly a small playground. With 200 to 400 billion stars, there's more than enough to explore for thousands of generations. The shift from we can explore the universe to we can explore our galaxy is less dramatic than the shift from Earth is all there is to there's an entire universe out there, and humans handled that revelation reasonably well. There's also the pragmatic argument that secrecy is simply impossible in modern science. Research on fundamental physics involves thousands of scientists across dozens of countries. Papers are published, conferences are held, and findings are debated openly. Any attempt to classify or restrict research on whether intergalactic travel is possible would immediately signal that something important has been discovered, triggering speculation and amateur research. The secret would be out before the ink dried on the classification documents. Citizen science and amateur astronomy have become increasingly sophisticated. Telescopes are relatively affordable. Data from professional observatories is often publicly available, and online communities collaborate on analysis. You can't hide cosmic truths from a species that has made space observation a hobby and a passion for millions of individuals. This actually suggests something hopeful about humanity's approach to cosmic questions. We're collectively committed to understanding our universe, regardless of whether that understanding is comforting or disturbing. The transparency and openness of modern science, while sometimes messy and contentious, reflects a cultural commitment to truth-seeking over comforting delusions. The balance between containment and curiosity ultimately tilts strongly toward curiosity for practical, ethical, and strategic reasons. Practically, secrets don't keep in modern science. Ethically, people deserve to know fundamental truths about their reality. Strategically, shared knowledge allows for better planning and response than siloed information. That said, there's a difference between transparency about scientific findings and responsible communication of those findings. Scientists and science communicators have a responsibility to present discoveries in context, with appropriate nuance, avoiding sensationalism while still conveying the significance. If research definitively showed that intergalactic travel is impossible, the announcement would need to include what this means, We can't leave our galaxy with any known or plausibly imaginable technology. What this doesn't mean, it doesn't mean we can't explore space. It doesn't mean interstellar travel is impossible. It doesn't mean we're alone or trapped in any practical sense. What we should do, continue exploring and settling the solar system, develop interstellar travel capabilities, search for life within our galaxy, and make the most of the vast cosmic territory available to us. The framing matters enormously. Humanity confined to single galaxy, cosmic exploration limited, creates a very different emotional response than Milky Way confirmed as humanity's permanent home, containing hundreds of billions of stars to explore. Both statements convey the same factual information, but one emphasizes loss, while the other emphasizes opportunity. The role of science communication in shaping public response to cosmic discoveries cannot be overstated. When handled well, even uncomfortable truths can be integrated into human self-understanding without causing widespread despair or nihilism. When handled poorly, even positive discoveries can trigger anxiety and backlash. The balance between skepticism and openness, between caution and transparency, between protecting people from uncomfortable truths and respecting their right to know, these tensions exist in science communication generally, but take on special significance when discussing humanity's cosmic future and limitations. Let's step back and really grapple with the scale of what we're discussing, because one of the reasons intergalactic travel seems prohibitive isn't just the energy or time required, it's the sheer vastness of the distances involved. To understand why we can't leave the Milky Way, we need to develop genuine intuition for cosmic scales, which are so large they resist human comprehension. Start with something familiar. The distance from Earth to the Moon is about 238,900 miles. When Apollo astronauts traveled there in 1969, the journey took about 3 days. That's a distance we can almost grasp. It's roughly 10 times the circumference of Earth. You could drive that distance in a car in a few months if there were a road. Now scale up to the Sun, roughly 93 million miles from Earth. Light takes about 8 minutes to make that journey. If you could drive a car to the Sun at highway speeds without burning up, it would take about 177 years. We've never sent humans that far, but we've sent probes that take months or years to complete their missions in the inner solar system. The outer solar system is where distances start becoming abstract. Neptune orbits roughly 2.8 billion miles from the Sun, about 30 times farther than Earth. Light takes about 4 hours to reach Neptune. Voyager 2 took 12 years to get there, launched in 1977 and arriving in 1989. That distance is already beyond human intuitive understanding, but it's nothing compared to what comes next. The nearest star, Proxima Centauri, is 4.24 light-years away, about 24.9 trillion miles. If you could drive a car at highway speeds to Proxima Centauri, the journey would take roughly 45 million years. The entire history of human civilization, from the first cities to the present day, represents about 1/8 of that journey. The Voyager probes, traveling at over 35,000 miles per hour, would take roughly 75,000 years to reach Proxima Centauri if they were headed in that direction, which they aren't. That's one star, the nearest star. The Milky Way contains between 200 and 400 billion stars, spread across a disk roughly 100,000 light-years in diameter. If you could travel at the speed of light, which you can't crossing the galaxy, would take 100,000 years. At Parker Solar Probe speeds, humanity's fastest spacecraft, it would take 145 million years. But here's where the scale truly becomes overwhelming. Andromeda, our nearest major galactic neighbor, is 2.5 million light-years away. That's 25 times the diameter of the Milky Way. If you could shrink the Milky Way down to the size of a dinner plate, Andromeda would be another dinner plate, about 6 meters, 20 feet away. The observable universe would extend about 465 kilometers, 290 miles, in every direction, containing roughly 2 trillion other dinner plates. Let's try another analogy. Imagine a grain of sand represents Earth. On this scale, the Sun would be about 2.5 meters, 8 feet away, and would be the size of a small orange. Proxima Centauri would be another orange about 670 kilometers, 416 miles away. The Milky Way would span roughly 163 million kilometers, 101 million miles. And Andromeda? It would be about 4 billion kilometers, 2.5 billion miles, away about 27 times the distance from the Sun to Neptune, but on a scale where Earth has already been shrunk to a grain of sand. These numbers stop being numbers and become poetry of emptiness, descriptions of a void so vast it makes mockery of human ambition. The space between galaxies isn't like the space between stars. It's almost perfectly empty, with perhaps 1 atom per cubic meter of space. It's cold, not just in the sense of low temperature, but in the sense of perfect isolation from any source of warmth or energy. It's dark, lit only by ancient photons that have been traveling for millions or billions of years. Now consider the time dimension. Light from Andromeda that enters your eye tonight began its journey 2.5 million years ago, during the Pleistocene epoch, when our ancestors were Homo habilis, barely recognizable as human. Every photon you see from Andromeda is a time traveler, carrying information about what that galaxy looked like when Earth's climate was radically different and humanity didn't exist. If we sent a signal to Andromeda today at light speed, it would arrive in 2.5 million years. If anyone there received it and immediately sent a reply, we would receive their response in 5 million years, roughly the amount of time from the common ancestor of humans and chimpanzees to the present day. A single exchange of messages would span more time than our entire evolutionary history as a distinct lineage. The universe is also expanding, which adds another layer of separation. Galaxies beyond the local group are receding from us, and the farther away they are, the faster they're receding. At a certain distance, galaxies are receding faster than the speed of light, not because they're moving through space faster than light, but because space itself is expanding between us and them. These galaxies exist beyond a cosmic horizon, forever unreachable even by light. The observable universe extends about 46.5 billion light-years in every direction, containing an estimated 2 trillion galaxies. Most of those galaxies are beyond the cosmic horizon. We can see them because their light left when they were closer to us and the universe was younger. But we could never reach them, even if we could travel at the speed of light. The expansion of space between us and them is winning the race, pulling them farther away faster than we could ever travel toward them. This is the cosmic context in which we exist. A universe so vast that most of it is forever beyond reach, structured by physical laws that create impassable barriers between its component parts. We're embedded in a web of space-time that permits local travel but prohibits global travel. That allows us to see vast regions we can never touch. Some find this overwhelming and depressing. The universe seems designed to show us wonders we can never reach, to make us aware of our insignificance and powerlessness. But there's another way to see it. The universe is vast enough that even one galaxy contains more stars than humans could explore in millions of years. The playground is smaller than we might have hoped, but it's still almost incomprehensibly large. Statistical realities reinforce this. If only 0.1% of stars in the Milky Way could potentially support habitable planets, that's still 200 to 400 million potential worlds. If humans could colonize just 1% of those, we're talking about 2 to 4 million human-inhabited star systems. At one new colony per year, that would take 2 to 4 million years to achieve, longer than our species has existed. The Milky Way is vast enough for countless human civilizations, separated by distances that would make them effectively independent, each developing their own cultures and technologies, each exploring their local neighborhoods while contributing to a broader galactic community. We wouldn't exhaust the possibilities of our home galaxy before the sun burns out, making other galaxies practically irrelevant to our actual future. The scale of the cosmos both humbles us and offers perspective. We can't leave the Milky Way, but maybe that's okay. Maybe the boundaries that physics draws aren't prisons, but gardens vast enough to explore indefinitely, bounded enough to give our exploration structure and meaning. After exploring all the ways intergalactic travel seems impossible, all the barriers and limitations, it's time to shift our perspective toward hope and possibility. Because while we may be confined to the Milky Way, confined is a relative term when you're talking about a galaxy containing hundreds of billions of stars. And the very fact that we're having these discussions represents an extraordinary achievement for a species that only developed agriculture 10,000 years ago. Let's celebrate what we've accomplished and what we've learned. Less than 70 years ago, we put the first human-made object into orbit. Just over 50 years ago, we stood on another world. We've sent probes to every planet in our solar system, landed rovers on Mars, deployed robots to study distant moons like Titan and Europa. We've built telescopes that can peer back to the early universe, detecting galaxies that formed when the cosmos was less than 1 billion years old. The Hubble Space Telescope, launched in 1990, has revealed that the universe is far vaster and more complex than we imagined. The James Webb Space Telescope, launched in 2021, is showing us the formation of the first galaxies with unprecedented clarity. We're studying exoplanets, planets around other stars, and finding that planetary systems are common, not rare. We've detected thousands of exoplanets, some in the habitable zones of their stars, some similar in size to Earth. This explosion of knowledge represents unprecedented international cooperation. When we discovered gravitational waves in 2015, it was the result of decades of work by thousands of scientists from dozens of countries. When we photographed the black hole at the center of M87 in 2019, it required coordination between 8 radio telescopes spread across the globe, effectively creating an Earth-sized telescope. The Large Hadron Collider at CERN, which discovered the Higgs boson in 2012, was built and operated by scientists from over 100 countries. This cooperation in the pursuit of knowledge is itself a form of hope. Despite political differences, economic competition, and cultural variations, humanity can work together when chasing fundamental truths about reality. The transparency of modern science, the open sharing of data and methods, the global collaboration on major projects, these represent civilization at its best. And the data keeps flowing. We're not just passively observing the universe. We're actively studying it with increasingly sophisticated tools. Radio telescopes scan the skies for signals from other civilizations through CT projects. Space-based observatories detect high-energy phenomena we can't observe from Earth's surface. Ground-based instruments with adaptive optics correct for atmospheric distortion, achieving resolution rivaling space telescopes. Interferometry combines multiple telescopes to achieve effective apertures spanning continents or even the Earth's diameter. This has practical implications for our discussion of intergalactic travel. Every year, we refine our understanding of physics, detecting new phenomena, testing theories to greater precision, exploring edge cases where our understanding breaks down. If there are loopholes in physics that would permit intergalactic travel exotic matter, manipulable spacetime, quantum phenomena that scale to macroscopic objects, we're more likely to find them through this tireless experimentation and observation. Consider what we've learned just about the interstellar medium in recent decades. Voyager 1 and 2 have now entered interstellar space, sending back data about the environment between stars. We're learning about the density of particles, the strength of magnetic fields, the presence of cosmic rays, and the interaction between the solar wind and the interstellar medium. This isn't just academic knowledge. It's crucial information for anyone planning interstellar missions, the stepping stones toward eventual galactic exploration. We're also making progress on the fundamental challenges that would need to be solved for long-duration space missions. The International Space Station has taught us an enormous amount about how Human bodies respond to microgravity over extended periods. We're learning about bone density loss, muscle atrophy, changes in vision, effects on the immune system, and psychological challenges of isolation. Each problem we identify is a problem we can start addressing. Closed-loop life support systems are advancing. On the ISS, we already recycle about 90% of water, including water from urine, sweat, and even humidity in the air. We're developing better methods for growing food in space, conducting experiments with various crops in microgravity. We're studying how radiation shielding can be made lighter and more effective. Each advance makes long-duration space missions more feasible. Perhaps most exciting, we're seeing the emergence of a genuine space economy. Private companies are launching satellites, delivering cargo to the ISS, developing space tourism, and planning missions to the Moon and Mars. SpaceX's reusable rockets have dramatically reduced launch costs, making space more accessible. Blue Origin, Rocket Lab, and other companies are developing new launch systems and space infrastructure. This commercial interest in space is crucial because it creates sustainable economic incentives for space development. When space becomes profitable, investment flows in, technology advances accelerate, and what once required government programs with billion-dollar budgets becomes achievable by private entities. The democratization of space access might be the single most important development for humanity's long-term expansion beyond Earth. We're also seeing increasing public engagement with space science. Millions of people follow space missions on social media, watch rocket launches, participate in citizen science projects, and consume content about astronomy and cosmology. This isn't just passive consumption. People are genuinely curious about space, excited about exploration, and supportive of funding for space science. That cultural enthusiasm matters because it shapes policy priorities and funding decisions. When people care about space exploration, governments and private entities respond. The success of missions like the Mars rovers, with their massive public followings, demonstrates that space exploration captures human imagination in ways that few other endeavors do. And let's talk about the silence from SETI. Yes, we haven't detected signals from alien civilizations, despite decades of searching. Some find this discouraging, suggesting we're alone or that civilizations inevitably fail before becoming detectable. But there's another interpretation. We've barely scratched the surface of the search space. The universe contains somewhere around Y stars. That's a trillion stars. We've carefully examined a few thousand of them for signs of technological civilizations. We've scanned certain frequencies and certain types of signals, but the parameter space of possible signals is enormous. We've also only been searching for a few decades, which is nothing in cosmic timescales. The absence of detected signals doesn't mean the absence of civilizations. It might mean civilizations are rare within our detection range, or that they use communication methods we haven't thought to look for, or that they're deliberately quiet, or simply that we haven't looked in the right place at the right time yet. The search continues, expanding in sophistication and coverage every year. Moreover, even if we're alone in the Milky Way, even in the most pessimistic scenario, where Earth is the only world that developed intelligent life in our galaxy, that makes our existence more precious, not less. It makes our responsibility to preserve and expand consciousness more important, not less. It makes our exploration of the galaxy more significant, not less. The data and the silence both carry hope. The data shows us a universe rich with planets, complex with structure, governed by comprehensible laws we're gradually uncovering. The silence means we're not obviously threatened by hostile aliens, not competing with other expanding civilizations for resources, not late to a galactic party that's been ongoing for millions of years without us. We're pioneers in a universe that seems, from our current vantage point, to be waiting for us to explore it. Whether we're the first, the only, or simply early among many, we have opportunities ahead of us that are limited only by our technology, our wisdom, and our willingness to work together toward long-term goals. The balance between skepticism and openness, between recognizing limitations and exploring possibilities, is where progress happens. We acknowledge that intergalactic travel might be impossible, but we don't stop investigating. We recognize that interstellar travel is extraordinarily difficult, but we don't stop preparing. We understand that space is vast and dangerous, but we don't stop reaching into it. This is humanity at our best, curious, ambitious, cooperative, and persistent. The very fact that we can have these discussions about cosmic boundaries and intergalactic travel represents triumph over countless obstacles our ancestors faced. We've gone from wondering what stars are to calculating exactly how far away they are and what would be required to reach them. That's extraordinary. Now let's get technical and explore exactly how we detect distant galaxies and what we actually know about the space between them. Understanding the science behind our observations helps clarify both what makes intergalactic travel so challenging and what we'd need to overcome those challenges. When we observe distant galaxies, we're primarily detecting light electromagnetic radiation across various wavelengths, from radio waves to gamma rays. The most distant galaxies we've detected are about 13.4 billion light-years away, meaning we're seeing them as they were just 400 million years after the Big Bang. This is possible because light travels at a finite speed, making telescopes effective time machines that let us observe the past. But here's a crucial detail. The galaxies we observe aren't actually at the distances their light travel time suggests. Due to the expansion of the universe, a galaxy whose light took 13.4 billion years to reach us is now roughly 32 billion light-years away. The space between us and that galaxy has been expanding while the light was traveling, stretching the light itself, causing redshift, and increasing the actual distance beyond what the travel time would suggest. This expansion is described by the Hubble-Lemaître law, which states that galaxies recede from us at speeds proportional to their distance. The proportionality constant, called the Hubble constant, is about 70 kilometers per second per megaparsec. This means that for every 3.26 million light-years of distance, galaxies recede an additional 70 kilometers per second faster. For Andromeda, which is relatively close at 2.5 million light-years, the expansion of space is negligible. In fact, Andromeda is actually approaching us due to gravitational attraction, and it will collide with the Milky Way in about 4.5 billion years. But for more distant galaxies, expansion dominates. At a distance of about 14.4 billion light-years, with current expansion rates, galaxies recede at the speed of light. Beyond that distance, galaxies recede faster than light. This doesn't violate relativity, because the galaxies aren't moving through space faster than light. Space itself is expanding between us and them. But it does mean those galaxies are forever beyond our reach, even if we could travel at the speed of light. We could chase them forever and never catch up, because the space between us and them is being created faster than we can traverse it. Now let's discuss detection methods. How do we know these galaxies exist and what we can learn about them? Optical telescopes detect visible light, revealing galaxy shapes, colors, and rough distances through redshift measurements. Radio telescopes detect radio emissions from various astronomical sources, including the neutral hydrogen that pervades galaxies. Infrared telescopes penetrate dust clouds and reveal the heat signatures of star formation and distant objects. X-ray and gamma-ray telescopes detect high-energy phenomena like black holes and supernova remnants. By combining data across these wavelengths, we build comprehensive pictures of distant galaxies. We can estimate their masses by observing how fast stars orbit within them. We can estimate their star formation rates by detecting ultraviolet light from young, hot stars or infrared radiation from dust heated by star formation. We can identify supermassive black holes at galactic centers by detecting intense radiation from material falling into them. But there's what we can detect and what we can't. We can see galaxies' aggregates of billions of stars producing immense amounts of light. We cannot, with current technology, detect individual planets around stars in other galaxies. The resolution required is simply beyond our capabilities. We can barely detect planets around nearby stars in the Milky Way. Detecting planets in Andromeda is currently impossible. This creates profound uncertainty about what we'd actually find if we could travel to other galaxies. We can estimate that Andromeda probably contains trillions of planets based on what we know about planet formation, but we can't confirm that any specific region of Andromeda would be hospitable to human settlement. Any intergalactic mission would be a leap into the unknown, guided by statistical probabilities rather than specific knowledge. Now let's discuss propulsion physics in more detail. Chemical rockets, which powered the Apollo missions, work by ejecting mass at high velocity. The maximum velocity you can achieve depends on the exhaust velocity and the mass ratio, how much of your initial mass is fuel versus payload. Chemical rockets have exhaust velocities around 4 to 5 kilometers per second, which limits their maximum delta V, change in velocity, to roughly 10 to 15 kilometers per second, even with enormous fuel fractions. That's sufficient for traveling around the solar system, but woefully inadequate for interstellar travel, let alone intergalactic travel. You need orders of magnitude more performance, which is why physicists and engineers have proposed alternatives like nuclear thermal rockets, which heat hydrogen to extreme temperatures using nuclear reactions, achieving exhaust velocities around 8 to 9 kilometers per second. Ion drives, which use electric fields to accelerate ions to very high velocities, 30 to 50 kilometers per second, but produce very low thrust, requiring years of continuous operation to achieve high speeds. Nuclear pulse propulsion, the Orion concept, which detonates nuclear bombs behind a spacecraft and rides the shockwave, theoretically achieving 3 to 5% of light speed. Fusion drives, which would use controlled fusion reactions to heat and expel plasma, potentially achieving 5 to 10% of light speed if the engineering challenges can be solved. Antimatter drives, which would use matter-antimatter annihilation for 100% conversion of mass to energy, theoretically enabling near light speed travel if we could produce and store antimatter in sufficient quantities. Laser sails, which use ground-based lasers to push lightweight reflective sails, capable of reaching 20 to 30% of light speed for very small payloads. Each of these systems faces formidable engineering challenges, and even the most optimistic ones only reach a small fraction of light speed. At 10% light speed, traveling to Andromeda would still take 25 million years. At 50% light speed, which would require exotic technology we can barely imagine, it would take 5 million years. The energy requirements scale dramatically with velocity due to relativistic effects. At low speeds, kinetic energy equals half the mass times velocity squared. But as you approach light speed, relativistic corrections become significant. At 90% light speed, the effective mass of an object is more than doubled, requiring correspondingly more energy for further acceleration. This is why even with perfect propulsion systems and unlimited energy, practical considerations constrain maximum velocities to perhaps 50 to 70% of light speed for crewed missions. The time dilation effects, where time passes slower for travelers than for observers, would help the crew, but wouldn't change the fact that millions of years would pass in the outside universe during their journey. Understanding these technical realities helps clarify why intergalactic travel isn't just an engineering challenge, but potentially a fundamental impossibility. We're not facing problems that can be solved with better materials or more investment. We're facing the basic structure of space-time and the laws of thermodynamics. So where does this leave us? If intergalactic travel is likely impossible, and even interstellar travel within our galaxy presents extreme challenges, what should humanity's strategy be for exploring and expanding into space? Let's examine the realistic near-term and long-term possibilities, looking at actual missions planned or under development and extrapolating from current capabilities. In the near term, the next 50 to 100 years, human space exploration will focus on the solar system. We're planning return missions to the moon through NASA's Artemis program, which aims to establish a sustainable human presence in lunar orbit and on the lunar surface by the 2030s. The moon will serve as a testing ground for technologies needed for longer missions: closed-loop life support, in-situ resource utilization, extracting water and oxygen from lunar regolith, radiation protection, and long-duration habitat systems. Mars remains the next major target. Multiple nations and private companies are planning Mars missions. SpaceX's Starship is explicitly designed for Mars colonization, with Elon Musk proposing establishing a self-sustaining city on Mars by the 2050s. Whether that timeline is realistic remains debatable, but Mars missions are technologically feasible with current or near-future capabilities. The challenges are enormous radiation exposure during the 6 to 9 month journey, landing large payloads on Mars, producing fuel for return missions, establishing sustainable food production. But they're engineering challenges rather than fundamental physics limitations. Beyond Mars, we're looking at missions to asteroids for resource extraction and planetary defense purposes, missions to Jupiter's moon Europa to search for life in its subsurface ocean, missions to Saturn's moon Titan to explore its complex organic chemistry, and potentially missions to the ice giants Uranus and Neptune to better understand these poorly studied worlds. These solar system missions will accomplish several crucial goals. They'll establish humanity as a truly spacefaring civilization, no longer confined to a single planet. They'll develop technologies and infrastructure needed for more ambitious future missions. They'll search for life beyond Earth, potentially finding microbial life in subsurface oceans or ancient fossils in Martian rocks. And they'll begin the resource extraction and industrial processes needed to build a space-based economy. Looking farther ahead, 100 to 1,000 years, we might see the first interstellar missions. These would likely be robotic probes rather than crewed missions, at least initially. The Breakthrough Starshot Initiative, backed by physicist Stephen Hawking and investor Yuri Miller before Hawking's death, proposed sending swarms of tiny spacecraft to Alpha Centauri using laser propulsion. Each probe would weigh only a few grams, but could theoretically reach 20% of light speed, arriving at Alpha Centauri in roughly 20 years, with an additional 4 years for data to return to Earth. Such missions would be scouts, gathering data about nearby star systems to identify which might be worth visiting with larger, slower missions. We'd learn about planets orbiting those stars, their atmospheres, their potential habitability, and whether any show signs of life or past life. This information would guide decisions about where to send more ambitious missions carrying larger payloads, terraforming equipment, or eventually human crews. Crewed interstellar missions would require generation ships or some form of hibernation technology. Generation ships spacecraft large, enough to support human populations for centuries or millennia, face enormous engineering and social challenges, but don't require any physics we don't understand. They'd need to be essentially miniature worlds, with closed ecosystems, industrial capability to repair and replace any component, and social structures that could maintain stability and purpose across hundreds of generations. Alternatively, if we could develop reliable long-term hibernation or suspended animation, crews could sleep through the journey, waking only when approaching their destination. This would require solving numerous medical and technical challenges, preventing tissue damage during freezing, maintaining life support systems that must function flawlessly for centuries, dealing with radiation damage during hibernation. But again, these are engineering challenges, not fundamental impossibilities. On timescales of thousands to millions of years, assuming humanity survives and continues expanding, we could spread throughout the Milky Way. This wouldn't be a coordinated empire or unified civilization. The distances and time delays would make central governance impossible. Instead, we'd see countless independent or loosely affiliated human or post-human cultures, each adapted to their local environment, each exploring their neighborhood of space, collectively forming a galactic diaspora. This expansion would proceed slowly by our current standards, but relatively quickly on cosmic timescales. If humans could establish one new colony per century, and each colony eventually launched its own colony ships, growth would be exponential. Within a few million years, a geological eye blink, humanity's descendants could be present in every region of the galaxy. But what about the species we'd become? Over millions of years, separated by vast distances with no interbreeding, human populations would likely diverge into distinct species. Colonists on high-gravity worlds would evolve different physiology than colonists on low-gravity worlds. Adaptations to different radiation environments, different atmospheric compositions, different selection pressures would drive speciation. The galaxy might eventually contain thousands or millions of species descended from Homo sapiens, as different from each other as we are from other great apes, but all traceable back to Earth as their origin. There's also the possibility of deliberate self-modification through genetic engineering or cybernetic enhancement. Humans might adapt themselves to space environments rather than trying to recreate Earth conditions everywhere they go. We might engineer radiation resistance, efficiency in low-gravity environments, ability to hibernate for extended periods, or countless other modifications that would make space travel and settlement easier. The line between biological and technological evolution might blur entirely. Uploaded consciousness, artificial intelligence, hybrid biosynthetic organisms, the possibilities expand as technology advances. The humans spreading throughout the galaxy in a million years might be recognizable more by their cultural and historical continuity with present-day humanity than by any biological similarity. And all of this entire grand vision of galactic expansion and evolution would still be confined to the Milky Way. Our descendants might explore hundreds of billions of star systems, establish civilizations on millions of worlds, diversify into countless species and forms, achieve understanding of physics and biology and consciousness far beyond our current comprehension, and still never leave our home galaxy. Andromeda and the trillion other galaxies would remain forever beyond reach, visible but untouchable, studied from afar but never visited. Is that enough? Does cosmic confinement to merely one galaxy diminish humanity's potential or achievements? That's ultimately a philosophical question each person must answer for themselves. But perhaps the more important question is, what will we do with the vast territory available to us? How will we grow and change? What will we discover? What will we become? The future implications of cosmic boundaries are less about limitation and more about focus. Knowing where we can go helps us plan how to get there and what to do when we arrive. And so we return to where we began, having journeyed through physics and speculation, through mathematics and philosophy, through despair and hope. We've explored why leaving the Milky Way might be impossible, not just technologically difficult, but fundamentally prohibited by the structure of spacetime itself. We've grappled with the vast distances, the prohibitive energy requirements, the cruel mathematics that make intergalactic travel seem like a fantasy rather than a future achievement. But here's what I hope you take away from this exploration. The Milky Way isn't a prison. It's home. Look up at the night sky when you get the chance. That band of light stretching across the darkness, that milky glow that gave our galaxy its name, that's our cosmic address, our neighborhood, our inheritance. It contains somewhere between 200 and 400 billion stars, each one a sun, many of them surrounded by planets, countless of those planets potentially suitable for life or settlement. That's not a small playground. That's a universe unto itself, vast beyond human comprehension, rich with possibility and mystery. We might never see Andromeda up close. We might never walk on shores orbiting stars in distant galaxy clusters. We might never meet civilizations that evolved under entirely different galactic circumstances. Those experiences might be forever beyond reach, lost to the tyranny of distance and the limits of physics. And yes, there's a melancholy in that recognition, a sense of doors closing that we hoped might stay open. But consider what remains open. Consider what we can explore, what we can discover, what we can become within the boundaries that nature has drawn for us. The nearest stars are just beginning to come within reach of robotic probes. Mars awaits human footprints. Europa's ocean holds secrets about the origins of life. The galactic center harbors a supermassive black hole we're only beginning to understand. Nebulae birthing new stars offer laboratories for studying stellar formation. Exoplanets with atmospheres different from any in our solar system challenge our theories of planetary science. We have barely begun to explore our own solar system, let alone the galaxy beyond. We've sent probes past all the planets, but we've only scratched the surfaces of a few. We've studied Mars more intensively than any other planet, and yet new discoveries happen with each mission, each rover, each orbital survey. What we don't know about our cosmic neighborhood vastly exceeds what we do know. And it's not just about physical exploration. Understanding the Milky Way means understanding galaxy formation, stellar evolution, the distribution of dark matter, the propagation of cosmic rays, the nature of the interstellar medium, the possibilities for life beyond Earth. Each question we answer reveals 3 new questions we hadn't known to ask. Each mystery we solve illuminates adjacent mysteries we didn't know existed. The search for extraterrestrial intelligence continues. We haven't found signals yet, but we've barely looked. Every year, SETI surveys become more sensitive, covering more of the sky, searching more frequencies, analyzing more data. The detection of even microbial life on Mars or Europa would revolutionize our understanding of life's prevalence in the universe. The detection of intelligent life, even separated from us by thousands of light years, would confirm we're not alone and provide perspectives on existence we can't currently imagine. Perhaps most importantly, we're learning about ourselves through these explorations. Space development challenges us to solve problems, to cooperate across national and cultural boundaries, to think long-term, to consider what really matters. Every mission teaches us something, not just about space, but about engineering, project management, international cooperation, and human capability. The technologies developed for space often find applications on Earth, from water purification to solar panels to medical devices. The limitations we've discussed tonight, the impossibility of intergalactic travel, don't diminish these achievements. They contextualize them. They remind us that exploration and knowledge have value even when they don't lead to infinite expansion. They suggest that wisdom might involve recognizing boundaries and working creatively within them, rather than endlessly pushing against immovable barriers. There's something almost zen about it, if you think about it long enough. The universe shows us almost everything through our telescopes. We can observe galaxies billions of light years away, witness events from the early universe, detect phenomena so exotic they challenge our understanding. But it keeps most of that forever beyond reach, not out of cruelty, but simply as a consequence of its structure. We're meant to observe, to understand, to appreciate, perhaps, but not to conquer or possess. Maybe there's wisdom in that cosmic design, if we can call it design. Maybe unlimited expansion across all galaxies would actually be unhealthy, leading to homogenization, to resource depletion on universal scales, to conflicts that span superclusters. Maybe the boundaries between galaxies serve a purpose beyond simple physics, creating diversity, protecting against existential risks, allowing each region of space to develop its own character and story. Or maybe it's not about wisdom or purpose at all. Maybe the universe just is what it is, structured by mathematical laws that neither care about our desires nor plan for our convenience. And maybe that's okay. Maybe we can find meaning and purpose within the boundaries that exist, rather than mourning the boundaries we wish didn't. So good night, Milky Way. Thank you for being our home, vast enough for endless exploration, bounded enough to give that exploration meaning. Thank you for your 200 to 400 billion stars, your clouds of gas and dust birthing new solar systems, your ancient globular clusters preserving memories of the galaxy's early days, your spiral arms tracing gravitational dynamics in visible form. We're still learning your secrets, still mapping your structure, still searching for your other inhabitants if they exist, still preparing to spread among your stars in the centuries and millennia to come. We might be confined to you for all of human history, but you're more than enough. You're home, and home is where we'll build our future, whatever form that future takes. To everyone watching, thank you for joining me on this journey to the edge of what's possible and the beginning of what's forbidden. What time is it where you are? What's your location? Drop a comment below. I love seeing our global community come together to explore these profound questions about our place in the cosmos. If this exploration sparked your curiosity or challenged your thinking, hit that like button and consider subscribing for more deep dives into cosmic questions. Share this with someone who loves space, someone who dreams big, someone who needs reminder that limitations can be liberating rather than confining. We can't leave the Milky Way, but maybe that's not a tragedy. Maybe that's just our story, and it's up to us to make it an extraordinary one. Good night, and keep looking up.